thank you very much. As you already heard, my name is Nadine Trummer and I am with the SLR group led by Michael Steindorfer. And today we're going to talk about our efforts to apply machine learning for the purpose of basic characterization. So let me get started by giving you an idea of what you can expect from today's talk. We're going to start out by getting to know space debris and learning what the issue with space debris is. And then we will make a short detour to machine learning so we can learn and understand which challenges and opportunities we can expect. Third, we're going to combine the knowledge we learned before, and we are going to talk about space debris classification. And here I'm going to introduce you to our latest publication. And lastly, I'm going to discuss future opportunities and ideas we have to discuss our current limitations. So to give you kind of an idea of what we are talking about, I brought 3 images with me. Here on the left-hand side, we have an artistic rendition of Envisat, which is a defunct satellite still in orbit. Here in the middle, we have a rocket body, which is quite a typical object that can be encountered in orbit. It is left behind during launch processes. This is a photograph taken during a flyby maneuver by the company Astroscale. And lastly here, we have a tool bag, and it has been lost by astronauts of the ISS during a spacewalk. And these are quite typical examples for space debris. But in general, we consider space debris to be man-made objects in Earth's orbit. They are non-functional. And this is the great problem with these objects, because they pose a threat of collision to our active satellites and also future satellite missions. And we also have the problem of a growing space debris population, because collision events can cause more space debris to be generated. And this effect is generally known as the Kessler syndrome. So let us have a quick look at the numbers. You do not need to read this table now. Just in general, here we see the total object count over all orbits and how it developed over time. So starting here with the first satellite Sputnik in 1957. And in general, the blue colored entries denote payloads, and payloads are functional satellites. And in red, we have rocket body and rocket mission related fragments and debris. And what might be interesting for us are the gray entries. These are unidentified objects, meaning we know that they are there. We know that they are larger than 10 centimeters, because that's the condition for a space debris object to be cataloged like this, but we do not know anything more about them. And the reason that they only seem to appear in the last decade or so is that our technology just got better at detecting unknown space debris. This has been taken from the Space Environmental Report. The ESA publishes it yearly, and ESA also has a close eye on the space debris numbers. So now we're going to discuss which behavior space debris can possibly exhibit in orbit, because as it turns out, there's a variety of possibilities. Space debris, for example, can exhibit different rotational behavior. We have the non-rotators, or for example, a slow rotator like Envisat, which rotates with around 130 seconds. And an example for a fast rotator would be Poseidon, which rotates with around 10 seconds, or has a rotation period of 10 seconds, which is quite fast. Further, the objects could be tumbling. This means they do not have a clean rotation around one spin axis, but rather the spin axis itself can exhibit some complex behavior. And this is important because this can cause complex signatures that are not easy to analyze. Here on the right-hand side, I have brought a figure that describes the inertial spin rate of Topex Poseidon over time. The inertial spin rate is essentially just a measure for how fast the satellite is rotating. And what you see here, after the end of the mission, the satellite has been speeding up. And this tells us that the behavior is not only unknown to us mostly, but it can also change over time. This means we need to observe space debris continuously to have a good idea of what is happening. And the cause for this changing behavior is the fact that the debris object interacts with its environment. For example, Earth's gravity and magnetic field, but in the higher orbit regimes, solar radiation pressure is also a driving force. In the lower orbits, like in LEO, the atmospheric drag is a huge influence. Then we have outgassing of components, and of course, there can be momentum exchange caused through collisions with debris or meteoroids. So now we know that it is quite important to know properties of the object, such as its attitude, which means how is it oriented in space, its spin properties, and its shape. And the reason why we are so interested in these properties is that they can help the orbit predictions. And orbit predictions, on the other hand, are very valuable for satellite operators because they help us avoid collision events. The problem is we can not easily find out these properties. And if we follow a very naive approach, we might have the idea, okay, I just point a telescope at the space debris object, and then I find out if it's a cylinder or a box, and I'll see all these properties. Unfortunately, that doesn't work very well. Here I have a CCD-based telescope image. So this image has been gathered through a CCD camera using a telescope. And what you see here, the space debris object is a tiny, tiny blob. And we also have some background stars passing through. This happens due to the exposure of the camera. Most space debris objects optically. And the reason is the atmospheric attenuation and, of course, the small object size. And this is where our SLR station comes into play. Today, I won't have the time to go into the measurement principle of our SLR station as a whole in detail, but I want you to understand what we are doing and how we obtain our so-called lightcurve data. As you maybe know, the purpose of our SLR station is to provide range measurements to satellites and space debris. And to do this, we target the object with a pulsed laser source at a fixed wavelength range. And we measure the time the photons need from our laser to the target where they will be reflected and back to us. And since the speed of light is known, we can calculate the distance between our station and to the target. And you will notice that only a very specific wavelength is actually needed for the purpose of SLR, but we capture all the light coming in. And the rest of the spectrum is used to gather light curves. So to summarize, we at our SLR station provide 3 data products, which are satellite laser ranging measurements, space debris laser ranging measurements, and single photon light curves. So at the end of the day, we have range and brightness information of the object. Today, I only have the time to focus on light curves in this talk. And light curves can only be gathered if the object is still illuminated by the sun. And I hope this figure makes it clear. We have the sun, the light source, and we, the observer, are already in Earth's shadow. But if the object is still illuminated by the sun and has not yet entered Earth's shadow, we can capture its brightness. Here on the left-hand side, you see our Contrabas telescope, which is the main telescope we do all our measurements with. And here we have an example for a light curve. On the x-axis, you see the time in seconds. And on the y-axis, you see the normalized counts per 10 milliseconds. That is just our unit, how we measure the brightness. So what we actually do is we count the incoming photons directly. And this is the advantage that we can achieve high sampling frequencies. So what you would normally do is you take an image like we saw before and extract the brightness from that image and do this for a lot of images, and then you get your light curve. We count the incoming photons directly, which is not usually done in our view. And let's have a quick look at what we are actually seeing here. We see some periodic increase and a few very narrow but steep spikes. The light curve you see here has been gathered or is of the object Topex Poseidon. You see an artistic rendering of the object here. And we have before the object is rotating with 10 seconds, roughly 10 seconds. And we can actually see this here. So we have a repeating pattern with a periodicity of roughly 10 seconds. So the first thing we learn here is that we can actually give an estimate of the rotation period based on the light curve alone. Second, we have some glint patterns. And glint patterns can often be linked to very shiny surfaces, like, for example, solar panels. So there's another hint how light curves can help us identify certain structures or give an estimated guess on which structures might be present on the object. Yeah, and of course, you see the object needs to be rotating in some form. Because if the object is always facing this with the same side to us, we won't have any additional information. So in this case, rotation is kind of a prerequisite to really extract information from light curves. And here I gathered some more examples of light curves. And we at Luftbühne Observatory built a light curve catalog we call the IWF Spark. It consists of roughly 6,500 light curves, and it describes 700 individual space objects. Here's another light curve of Topex Poseidon. In the middle, we have the light curve of a rocket body. And down here, we have the light curve of a GLONASS satellite, which exhibits a lot of glint patterns, which can be linked, for example, to solar panels. These are my favorites, by the way. So we have this light curve catalog. Of course, not all light curves are of this good quality. But in general, we have a catalog. And for those of you who have some experience with machine learning, pattern recognition, computer vision, you might already have started thinking, okay, what can we do with like a catalog? And this is the place where I want to slowly transition into the machine learning part of the talk. But let's take a quick brief. So we learn the space debris characteristics, and then we are interested in certain characteristics. We also know that these characteristics might change over time. And we know that certain characteristics can be extracted or learned by analyzing light curves. And lastly, we have a light curve catalog at our hand. So now we can ask the question, can we characterize space debris objects from measured light curves using machine learning? And you will notice this word is quite vague. That is something we need to work on or to make more concrete in order to be able to actually design tasks. So I want you to take a quick detour with me in Machine Learning 101. Today I won't talk about any specific machine learning model. I just want you to understand, if you happen to not have ever heard about machine learning, I just want you to understand or have a rough idea about the challenges we face and what we need to work on these challenges. So in machine learning, very roughly speaking, we differentiate between supervised and unsupervised methods. Today, I won't talk any further about unsupervised methods, but in general, they work with unlabeled data sets and go more in the direction of structure recognition. I'm more interested in supervised learning approaches. And here we differentiate between regression problems, where we want to predict a value. Value, for example, to prediction would be the spin period of a satellite. That is a real number we want to predict based on our input. And then on the other hand, we have classification problems which aim to predict a class. A class, for example, would be, or a class task would be to differentiate if the object is of cylindrical shape or a box. That would be a class task. But no matter which task we choose in the end, these are the three things we need to work on the task, which is a clear objective, a labeled data set, and sufficient data quantity and quality.
Maybe a quick question to that. How many labeled cases you have? I mean, where you know what the object really is?
It depends on the task. So it really depends which task you choose. Because for most objects, I have information about the general shape. But if I want to ask about the true value of the spin period, I don't have the means to fly up there and look at the object. So it depends on the task. So this is why it is so important to think about which task is realistic to tackle. How am I going to get my labels for the task? And lastly, do I have enough sufficient high quality and quantity data? So this question is important because we need to ask ourselves, or I need to ask myself, if I want to characterize space debris, what is realistic and what is smart to do?
Say out of the 6,500 light curves you have, how many are in any way labeled?
Official labels. So in our current study, we choose a subset of 850 light curves where I had labels, very clear labels. If I wanted to push it, I can maybe come up with more labels, but it really depends. I'm coming back to this. I'm going to come back to this. But I first wanted to introduce the task. We're going to have a at-hand example of this. Where was I? So we're going to transition to the current paper we have been working on, we have published. And the question of this paper was more concerned, or among other questions, was concerned with asking, okay, can machine learning models accurately characterize single photon space debris? Light curves, because that hasn't been done before. We were not completely sure of single photon space debris light curves suitable for the machine learning approach. And for this, we needed to answer these three questions. We needed a clear objective. And I decided to demonstrate the suitability of single photon space debris light curves by classifying individual objects. Do we have a data set? Yes, label data set, yes. We can retrieve labels using the NORAD ID, and this is a internationally identified entry where we can get data about the catalog objects. And lastly, do we have sufficient data quantity and quality? And in this case, as I just mentioned before, we chose a data subset where we were very sure that the data was high quality. And this is our application. And our approach was to test several models and also pre-processing steps on the different tasks. Here are the models we used. And I'm not going to go through the whole figure, but I want to point out a very interesting branch. So here you see our approach in general. And I want to follow this branch here to the decimation. This means we downsampled the data due to performance reasons. And here we tried a pre-processing step, which is called feature extraction. And as it turns out, this branch here led to the best results. And I want you to have a quick look at how feature extraction works. So first we did the test run where we fed the machine learning model with just the light curves. That was our baseline performance. But then we added a feature extraction step. And the feature extraction step essentially extracts a feature vector. Examples for features would be the maximum or the mean of a light curve. These are very simple examples, but essentially the vector denotes statistical properties of the light curves that describe the light curve very well. So instead of feeding the raw light curves to the machine learning model, we trained it on this feature vector. And this way, we achieve very satisfying results. And most interestingly, a random forest classifier, which can be seen as a more traditional machine learning method, performed as well as a convolutional neural network, which is a deep learning method. Just to give you a number, the accuracy on a 5-class task was with 90.7%. And when comparing that with other literature, that is quite satisfying. And the feature extraction pipeline we used was from a third party, so to say. It has been established in the time series analysis domain quite some time ago in 2018. And I want to give you a hands-on example of what such a task might look like. So here I have my 5 classes. I decided to classify families of objects. For example, here the JSON family consists of JSON1 and JSON2, which are defunct satellites. Then we have the GLONASS constellation, which is also a constellation of defunct satellites. But this group here is made up of 9 individual objects, and so on. And so we arrive at the 5-class task. We don't need to pay any special attention to this table. But what's important for you to see here is that the classes are unbalanced. And this means JSON1 and 2, the JSON class, contributes around 30% of all light curves. And keeping that in mind will be important for interpreting our results. And we decided to visualize our results using a confusion matrix. The confusion matrix gives us an idea if samples have been classified correctly, and if they have been classified wrongly, it gives us an idea where the wrong samples have gone. So if you have a perfect classifier that makes no mistakes, the diagonal would show all ones. This means every Topex Poseidon sample has been correctly classified as Topex Poseidon. Every JSON sample has been correctly identified as JSON, and so on. So that would be a perfect classifier. And you can see for most of the samples, we are close to 1 on the diagonal, with one exception. And that is the Atlas class. And Atlas contains rubber bodies. And why confusion matrices are so great, we can actually see, okay, 70% have been classified correctly, but where's the other 30%? What has happened? And seeing that, we can say, okay, around 30%, 0.27, have been wrongly classified as GLONASS satellites. So clearly there's something going on. And when looking at the class distribution, okay, Atlas is a minority class. Minority classes are always a little bit of a problem because they tend to be misclassified a little bit more. And so, yeah, and also we see JSON is also a majority class, but Atlas has not been classified as JSON. And I think the reason why this happens becomes quite clear when we look at the light curves directly. The red and black light curves belong to the GLONASS class and AEO5. So the blue light curve belongs to the Atlas class. And what you see here, a human might still be able to differentiate between these, but they look very similar. So this is also a lesson or quite interesting to look into. If the machine learning model makes mistakes, are the mistakes sensible? Do they make sense to us, or does something completely unexpected happen? So in this case, I would argue the mistake makes sense because Atlas is a minority class, and the light curve for Atlas also looks very similar to the GLONASS class. So this mistake happening here is unfortunate, but it does make sense within the task. I would be more worried if I cannot find out why the machine learning model is making the mistakes. So there's something to be learned by looking about the looking on the misclassified samples. Just a little bit, yeah, for human they look different, but you have to remember that the feature extraction. Sorry, I'm just answering the question in the chat. So feature extraction, you as a human would see, okay, that's obviously a steeper glint or so, but we do not know if the features we chose in the feature extraction pipeline can accurately represent the difference between these light curves. So of course, as a human, you might look onto them and say, of course, but that's how we human works. And so this is actually an incentive for going back and thinking, okay, how can we improve, for example, the features we choose to represent this difference? So our key findings of our general paper were that the single photon light curves, yes, they were suitable for the machine learning approach. Results were quite satisfying in comparison to the rest of the literature. They suit very well, or fit very well. And we also found that feature extraction can significantly boost our classifier's performance. But also we have some limits and challenges. As already mentioned, obtaining the labels and ground truths is difficult and sometimes quite labor intensive, and in some cases even impossible. We have immense classes, and our latest study was done on a well-behaved subset. And I want to take the time and address the limitations and give some ideas on how we might circumvent them. First of all, we can explore additional input data, such as, for example, our SLR data, so the range information. Then we can add vectors and angles describing the observation geometry, so we have usually access to these. And lastly, we can also think about simulating light curve data, of course. We also have some ideas on models and approaches that could follow or address these concerns. We can do a follow-up study using a neural network architecture, using a larger part of the data set. There's also the possibility of transfer learning. And transfer learning is a chance to include simulated data into the training process. The idea behind transfer learning is to pre-train a neural network on simulated data and then fine-tune it using real data. And lastly, we have physics-guided machine learning, and this would allow us to include the knowledge of physics into the machine learning model, because we have certain ideas about how the objects are supposed to behave due to theoretical mechanics and our general orbit modeling. So we could think about how this knowledge can be included in our models through equations. And I want to touch on the input data or the simulated data as input data. And I'm currently working on a light curve simulation program. And I want to give you a very rough outline of what that actually means. So I'm currently I have implemented a means to simulate the position in space, so how the object moves across its orbit. We can simulate different rotational states, and we can also simulate simple geometries like cylinders and boxes. I've currently implemented a flat facet model. This means based on the light vectors and incoming light and equations, I can calculate the brightness of an object through flat facets. And there's also the option to do a full 3D image render of the object and then extract the brightness. And lastly, there would be the option of including a sensor model just to make the light curves more realistic and similar to the real light curves. But the simulation will be an important tool in the future I'm currently working on. Here's a little preview. This is quite, here is a simulated light curve of a box. Then here we have vectors of the observation geometry and how they change over time. So this could be a possible input for the machine learning model to give it more context. And this is the trace of the satellite across the sky. This is just more for human interpretation. So just to give you an overview of the benefits, the simulation would actually provide us with a large quantity of labor data, because in the simulation, we have access to all the information and all the parameters. Second, we would have sufficient quality and quantity of data. We can generate as much data as we need. And of course, the additional data which can generate, for example, the orbit vectors, and we also have flexibility in the tasks. And the challenges for the future would be to bridge the gap between simulated data and real data. So that is the next big issue, or generally an issue in the community that is currently tackled. So how to include the simulated data into the planning process. And I already told you there's transfer learning and there's physics-guided machine learning that can be pursued. And I want to close the talk, bringing our end with an outlook. Today I talked about classification and that I'm, for example, interested in the shape of objects. But there's a bigger picture why we are making these efforts. Having knowledge about the spin behavior and the type and the geometry of an object is important input for our larger effort, so to say, which is attitude estimation. We want to know how the object is oriented in space, how its spin axis is oriented, and what its spin period is. And yeah, these classification results, or knowing the geometry, would be important because there can be ambiguities in solutions and they can be better interpreted this way. And the interesting thing about simulations is that we can test approaches and ideas. For example, the physics-guided machine learning, this has already been kind of explored by a group. And by simulating data, we can test our machine learning models without the need for having labeled data. We can test our ideas and hopefully come up with good solutions for attitude estimation that can then be applied someday to real data. I want to thank you for your attention, and also want to thank my collaborators who worked with me so far, which are Amit, Michael, and Janne Helwig. So thank you for your attention, and I'm happy to discuss with you now.
Yeah, thank you for the very interesting talk. Yeah, I think there is room for questions of the interested audience. So, you go first.
Thank you. That was really interesting. So I read recently about this cool American space plane thing, the X-37. Are you worried about stuff like this sort of polluting your data? Because of course, not everything in space stays in nicely one orbit, and actually.
What do you mean
So yeah, so there's I think it's the X-37 or something. They have this very cool space plane, and one of the things that is interesting about it is that it can change its orbit quite dramatically. Mm-hmm. Are you worried about the impact of these things on your data set, or are they already flagged? Like, you know.
When it comes to the data collection itself, I don't think there will be an influence. Our data is, or the brightness we capture is narrowed by the field of view. We can adjust. So I think if this thing or these things ever come into measurements or field of view, I think the probability of that happening is not high enough to have an impact on the whole data set.
Okay. Thank you.
I think, yeah.
Yeah, just a detailed question about you said this feature extraction. So you gave examples, maximum and mean. Okay, that's quite trivial.
Yeah.
But I guess, so how many of these features are there, and can you define your own, or is it some kind of package you use that is kind of pre-made, or I mean, yeah, what kind of features and how many?
Currently, we are using a pre-made package, Python pipeline. It would technically allow to include my own features. But for the first study, we used a pre-made feature extraction pipeline that has been established in the time series classification domain. So it's not a random choice, it's quite established, or at least from the literature. Let me touch on sorry, you're going to see all my slides. Don't be afraid. the feature extraction pipeline has some for our study provided me, I think, with 360 features, if I'm not mistaken, somewhere in this ballpark. And this is a figure which lists, or don't read that for your own sanity. This figure lists the correlation between the features the pipeline has shown us. So there's quite a few entries that have large correlation. And what this means is technically the feature space can be reduced even more. And this happens because features are extracted using formulas, but different parameters are applied. The feature is extracted for, let's say, 5 parameters. And these features with the different parameter combinations are all used for the training process. So this is, for example, why this correlation here for certain features happens. This here is assumed inversion of up here. And you see here we have strong correlation, but it's essentially the same feature, just calculated with different parameters. And yeah, that's essentially what the feature space looks like. And coming back to your question about custom features, we saw that the feature extraction is not like the like there's still room for improvement. And for example, it would be interesting to make or think about, well, which features are very specific to the task we can add as certain properties, which the classifier might benefit from.
It's a kind of two-step characterization. So from the light curve, you produce these numbers, which is already a characterization. Maybe they not all have a meaning, like the mean or the whatever frequency might be also something. And then you apply machine learning to these kind of simplified quantities.
Yeah. So the idea between of the feature extraction is actually to reduce the space the machine learning model needs to learn on. But you are right. So TS-Fresh also excludes features that are redundant and have no meaning to some degree. So that's something the extraction pipeline does. But of course, the extraction pipeline does not know about our problem. It does not know which model we are going to use. So of course, there's still some correlation to be found.
Sorry, there's also a question online.
Question I have, right, again. And you can get 88% using a CNN on these features.
Yes, that was the same setup.
Yeah.
And the model was different.
Okay.
So I think with CNN, we have to add that the model, there's quite the quantity of training data.
I don't know. Can you hear me?
Yes.
Yes. In my opinion, it doesn't make sense because the CNN is a convolution. So it means it uses like a moving operation, like a moving mean, but more complex over this feature. And the fact that we will make a given computation between the 3 first features to assume that it will be related in any way with the 3 last one or any other combination of 3 features. I think CNN was quite an error here. And my question is, did you try to use something, I would say, more simple nowadays, just put in and apply like a transformer on the original raw data? You just take the signal as it is and dump it in a transformer and just check the result.
Concerning your last point, no, we did not go into the transformer direction. With CNN, it could be that I'm mixing up results right now from my memory. But yes, of course, you're right. The CNN essentially it's a convolutional operation that works better by feeding the one-dimensional light curves. If I have mixed up the results, give me a second.
We already have done this CNN on directly on the light.
Yeah, we have done the CNN directly on the light curves, and we have different approaches, and we wanted to make a comparability or between the approaches. So I'm not sure if I'm mixing up the numbers right now, so sorry about there, but in general, I agree with you that the CNN operation on the features, of course, the CNN on the row light curves would make more sense because the CNN does the convolutional operation, which is more to this image interpretation of the whole task.
I think you have all the overview over the different approaches you talked during the paper included in one slide earlier. So maybe this would be a starting point to.
And the answer is the CNN has been applied to the original data and not to the downsized data. So that answers this a gentleman's question.
Yeah, so this would cover case 2 where we actually own case 1 and case 2 where we take the light curves themselves and feed them to the random forest classifier, XGBoost and CNN. Yeah, sorry. And then there's the sub case where we choose feature extraction, and because the feature extraction was of course more relevant for the random forest classifier. That was the thought behind that.
If I may, because this was a sort of related question, I think, and also goes into Peter's point. So I'm not entirely sure how this TS-Fresh works, but to what extent? Because I could imagine, like, also looking at the examples you showed, a lot of the data is periodic or semi-periodic. I could imagine, like, throwing a Fourier transform at this would already give you like a lot of information. That it seems, if I read your figure later on in the supplemental slides, actually are not being used by TS-Fresh. So things like just the periodicity of the light curve, I couldn't spot in there at least, but there were 100 labels.
Yeah, that's why I actually extracted a summary. Sorry.
No.
And I was interested on which features of the which features are especially important for the classification. So this is the importance for the random forest classifier. Fine. So here, just to give you a quick idea, we worked on 3 tasks. And the family task is what we discussed in the feature confusion matrix before. So these are 3 different tasks we worked on, and these results are all on a random forest classifier. And I had a look and thought about, I asked, which kind of features are more important for the classification. I did not have the time to look into the mathematics or the meaning of all features yet, but we have a Fourier transform coefficient. The autocorrelation might tell you something, or for example, the number of peaks. So these were the general importances of features that seem to be important across all tasks. But I'm sorry, I can't tell you the details or the math details or the interpretation of all these features just yet. I did not.
I wouldn't deflect that on you. And like I said, also like obviously that there are strong periodic signals in there, right? But just looking at it by eye, also there are very clearly very non-periodic things in there that are. I can imagine like this is a really difficult task to deal with because your brain may suggest some ideas for what works, but.
Concerning the periodicity, I showed today very nice light curves to you. Yeah, periodicity, and which I thought would look good. And of course, there are light curves that are messy. For example, NVSAT has a slow rotation period, so it is quite difficult to capture even a whole rotation when observing the object. And it, the signature does not look good at all. So there's also light curves that do not have this clear periodicity going on.
Maybe also one small comment on the periodicity. So from light curve to light curve, even of the same object, the rotation period can change due to apparent rotation. You can assume that the object is moving while it is rotating. So this actually stretches depending on the rotation axis, the rotation period. So even in different light curves from the same object, there can be variation. Yeah.
That's a question about the number of light curves. So how long does it take to generate the 6,700 light curves? Just to get a feeling. So.
The measurement started with the Coke experiment in 2015, and the light curves considered go until February 2024.
So it's not easy to double the number of light curves, so to say.
We have some thoughts and efforts in place on how we can increase our light curve output, because with the current numbers and the current speed of light curve gathering, and you have to think about that not all light curves are beautiful and nice quality, so on. We are thinking about doing a dedicated campaign. Can I mention also? Now we have a second telescope at our facility that is currently unused, and we were thinking about efforts of automating the light curve routine to some degree, choosing certain objects that will be relevant in the future, and essentially take measures to increase the number of light curves available to us. So.
Yeah, thanks for a nice talk. So my question was very similar. So how, if you have like, I don't know, 100 or 1,000 new space debris every year, how much time do you need to characterize all of them, or is it sufficient? And a follow-up question is, what's the gold standard in characterizing space debris? Like, for example, what does SpaceX use so that their rockets don't collide with random things in space?
I'm very sorry. Can you? What was the first question?
Yeah. So if you have certain number of space debris which keep accumulating, yeah, can you keep up with them with your current facilities, or like what do you need?
The keeping up with them, I think, is impossible. There's not a lot of facilities that do light curve measurements. We know the space debris is there. We have some rough orbit predictions. I think it would be better to focus on targets that are of concern, targets that are short of breakup, because if they rotate very fast, they can break up because of the energy and so on. Targets that are in LEO, because LEO, low Earth orbit, is very crowded, full of rocket bodies. And I don't think we have the capability anytime soon to track all targets to that extent. So, yeah.
Follow-up question. Yeah, thanks for that. Follow-up question was that what's the gold standard? What do NASA use? People like that, do they use radar? I don't know what they do.
To my knowledge, radar is used to find space debris in the first place. So detect, yeah, we have a cross-section of something is there. And for distance measurements I should need to go into SLR here. So normally when you do distance measurements to active satellites, they have something called retroreflectors. And these are, let's call them tiny mirrors that ensure enough signal is returned to us. So they make the SLR routine very easy. With space debris, such as rocket bodies or fragments, you do not have that luxury. So you do not have any reflectors on them. And this is where space debris laser ranging comes in. And we have a very powerful laser. We shoot up there and illuminate the object to make sure to get enough signal back. And with the possible accuracies, you need to help me out. What's with space debris laser ranging? Accuracy?
Yeah, we are in the meter level for our current setup, and yeah, going to even millimeter level with the megahertz setup in the future. Yeah. But yeah, I mean, in terms of let's say gold standard for collision avoidance, NASA and so on, which they are using. So they are relying on radar data. Yes, they have this radar fence, of course, very, very expensive and very large telescopes. They are using them for tracking a lot of objects. Publicly available, the catalog is in the order of, let's say, 100 meters, could be even worse accuracy for the orbit predictions. Yeah, we assume that there is something more precise, which can be used from radar data, but this is what's let's say publicly available. So
that's not public. Yeah, what they do.
Okay. Yeah, so I assume that there is something more precise existing as well.
Yeah, I think it's also military adjacent, right?
Not necessarily even adjacent, just that, right?
Just go back to the gold standard. I think our SLR group is to some point setting the gold standard, because every time something goes terribly wrong, they get a call, can you have a look? So And I think, yeah, you are really leading the field. And I would also suggest to have a look at the wonderful Nature paper you just put out for the megahertz laser. I have a very unassuming question for you, actually. You said, you showed your wonderful light curves, which are wonderfully periodic, and everyone thought it's such an easy task to classify it until you really made sure that this is actually the nice part of your sample. You said you liked the glint pattern most. Why is that? So this was your favorite light curve.
So to understand this, we need to how do I explain that? Give me just a second. So when talking about reflection, we differentiate between or very roughly, we differentiate between diffuse reflection and specular reflection. And you can imagine that on a matte surface, when light, for example, this table here, that's a matte surface, we are not blinded by the incoming light. But on shiny surfaces, if the angle of incidence equals, or the observer is looking at the angle of incidence where the light comes, and we can have a total reflection, so to say, or a specular reflection. And this is, for example, if you turn a CD in the light, like a disk, and at a certain angle you will be blinded because their specular reflection occurs. So a lot of light is directed into direction. And this is essentially what happens here with these glints. So of course, Topex Poseidon has a very periodic pattern. Here, these increases just tell us, okay, more surface area is facing us. But these glint patterns, they are very steep and very spiky. They usually indicate that the solar panel is facing us. And from my experience, this is always the indicator that the object is actually visible and that it is man-made. I'm aware that saying from my experience here is a bad indicator, but generally we need to have some manual inspection of light curves to determine if the object is in field of view or not. And this is why we reduced the IWF spark from this respectable number of light curves to just 850, because here I was sure that the objects were in field of view and actually visible. Does this answer your question, or? Thank you.
About disco light, or
Yeah.
I think it was called disco light or disco ball, or
What you say?
I mean, it's just
Yeah.
long time ago, but I think it's still used. So you get this very clear reflections, and thousands of them.
Yeah, I should have brought the Archie curve.
Actually, from Archie, I mean, this is basically just a sphere consisting of retroreflectors and mirrors. And with the single photon light curves, we were able to really detect one glint of one mirror. And even there was a study where the reflection of one mirror, or the reflections of the individual mirrors were characterized. And yeah, it was possible to conclude that there are defects on the individual mirrors. I mean, this really points to the high resolution of the single photon light curves, which is basically the main feature as compared to CCD data, the high temporal resolution we can get.
Okay. You say it. You say it. You say it. Wait a minute.
So it is possible to get a picture of satellites. I believe this was, if I have read it correctly,
Yeah.
Pictures of satellites or space debris.
Okay, as you said, that we cannot take a picture and determine what the telescope from Earth. But can we not use telescope in space to do that?
Yeah. First of all, we cannot take pictures of most space objects because, of course, like huge things like the ISS will still be visible. And yes, that's actually an idea to just send a telescope dedicated to space debris survey up. The first question would be who's financing the telescope? Because it's the world's trash, not just Austria's trash or Germany's trash or Elon Musk's trash. But also, yeah.
So probably Caribbean, right?
I think it would also be a question of how many space debris is visible to the space debris telescope at its position. And second, would we be able to really gather enough data across the whole population to justify the cost of sending a telescope up? So that's kind of the considerations I have been thinking about in that regard. I have not thought about any scientific reason or like optical reason not to send it up. Yeah, I think I don't think it would make sense given how large the population is to send a single telescope up. But that's my thoughts on the question.
At a risk of bringing politics into it, but I can imagine there is also a political component here where certain countries are maybe not that happy if you're looking at, you know, things that are not debris.
The SLR station has a blacklist of satellites we are actually not allowed to target. Or
Yeah, amazing. So basically the targets we are looking at, they are available from a public catalog. I mean, of course, you need some predictions to be even able to track targets. Yeah.
No, as you argued earlier with the few being there. Yeah.
Okay. Just there's room for one question, 1 minute, one question.
Nice talk. I don't have any question. Am I allowed to answer to a question which was asked online?
Yeah, of course. Yes, please.
So we do have tried advanced CNN model like ResNet, and also we have tried this new architecture that is called CAN, Kolmogorov node network, and also we tried swing transformer. So the point is that we already have results in terms of transformer advanced CNN architecture. But why you're not considering that as the best solution right now? Because we have a limited training data set. So once we have a more data set, then probably we could actually publish those results in terms of adding more training data and try to compare between the low-level machine learning, ML, for example, random forest, all those algorithms with or against this advanced model like transformer. So I would just to mention that this is a sort of update from our side that yeah, we already have done those results. At least we have the previous results with those architectures.
Thank you.
I think we can close.
Yeah, so I believe, yeah, we can close the session this way. And okay. Yeah, thanks to Nadine again.